Okay, so let's say there are n numbers given to you, and each of them is a1, a2, a3, so on up to an. Okay, and you need to find how many of the subset sums of these numbers will have sum less than equal to some given input x. Okay, so you're given n and x as input, and then there are n numbers. Find out the number of subsets of this particular set. So this n number forms a set. Okay, find out the number of subsets whose sum is less than equal to x, right? So there would be 2 to the power n subsets, right? Find out how many subsets of that would be formed will have sum less than equal to a given number x. That x is fixed and is given in the input. Okay, so let's say you are given the set 1, 2, 3, 4. Okay, so let's take a bit smaller. So 1, 2, 3, of course, 1, 2, 3, 4 will have 16 numbers. So 1, 2, 3. So you will have 0, 1, 2, 3, 3, 4, 5, 6, right? These are the 8 numbers that will generate. These are the, like, you form subsets. Let's say you form a subset 2, 3 and take its sum into consideration. Okay, this 5. So out of all these subset sums, how many subset sums would be less than equal to x? That's what we need to find. Make sense? Is the question clear to everyone? Can I have a plus one in the chat if this is clear? Right? So out of these 2 to the power n, find out how many of them follows this particular condition, right? So let's start with this. Let's say n is up to 20. Okay. So let's say n is up to 20 and we need to find number of subsets. So how do we solve this? It's not bit masking. It's most like brute force, right? Like you iterate on masks. Okay. Yeah. So that is something we would be talking about. Let's talk in terms of code itself. Okay. Okay. First, so we can do this in recursive styles. Okay, you can do this in recursive styles, but today we'll be talking about the iterative style of brute force. Okay, so we had seen a lot of problems of recursion, and I think there were a lot of recursive practice problems as well. So I think all of you must have got a hang of how backtracking brute force works, right? That you keep, so it's very easy to say, write this particular in a recursive brute force that, okay, let's say recursion that you have seen up to ith element and your current sum is sum. Okay, so then you either include ith element, so you go to I plus 1 comma sum plus x, sum plus ARR of I, or you go to I plus 1 and you don't include it, right? So these are the only two possibilities. So these would generate the subsets. These are the two subparts that you go into, and as soon as the sum gets greater than x, you can prune that off, of course, because let's say the numbers are all positive. So let's say the numbers are not all positive, so you cannot prune right now. Okay, so let's say we don't know whether the numbers are positive or not. So let's say we cannot prune directly. We can of course prune if we sort the array, but let's forget about pruning. In the worst case, we will have to go into all subparts, right? Let's say all the 2 to the power n has sum less than equal to x. X is a very large number, so in that case, all of them will be visited, right? So all of these things would be there. So finally you will get to, let's say, some 20 comma sum, and then at that leaf, like that would be like the base case, and then you will check whether sum is less than equal to x, and if this is true, then you will do answer plus plus, right? This type of brute force we have already seen by now, and I hope you are now comfortable in writing these kind of brute force, right? Just whatever is needed, keep it in parameter and write a brute force, right? So this is the recursive style of solving the problem, right? This is the recursive style. So today we'll be talking about the iterative style of the same problem, and places where, like, for this problem, it's very easy to write a iterative code. Okay, so we will also talk about iterative code. So how do we write an iterative styled brute force? Simply use mask. So what is mask? Okay, if you remember, we talked about mask in bit manipulation. So it's nothing but having zeros, ones, zeros, one, right? So this means this is the 0th place, this is the first place, this is second place, third place, fourth place, right? We know that the bits can be ordered, like marked as the positions, and then we can check whether it's 0 or 1 at some position, right? So if it's 1, then we know that we say that, okay, that element is taken, so take a of 0. If this is 1, that means take a of 2. If this is 1, then take a of 4, and then add them. Okay, so this particular element corresponds to the set 0, like a of 0, a of 2, a of 4, right? And its sum will be this particular sum. So as you can see that, let's say there are 5 elements. So let's say there are 3 elements. So there are only these combinations possible, right? These are the only combinations. And if you see that, if you write them in terms of their integer values, like if this is the binary representation, like this means whether a of 0 is present or not, this means whether a of 1 is present or not, this means whether a of 2 is present or not, right? There are the 3 numbers, and if we convert them to numbers, there is a continuous series of numbers from 0 to 2 to the power n minus 1, right? So in this form, what we can do is, if we want to iterate on all subsets of n numbers, what we can do is we can loop from 0 to 2 to the power n minus 1, okay? And this would be our mask, okay? And for every mask, we know that that corresponds to one particular subset, right? And from that particular subset, if we can just iterate on the bits and find out the sum of whichever is 1, right? So if this is 1, then take that corresponding element sum into the account. Is this idea clear? Like what we are doing right now, this mask idea? I think we like very briefly talked about this when we were discussing bit manipulation, but this is the iterative style in which you can write this particular thing, that iterate on all numbers from 0 to 2 to the power n minus 1. There will be a one-to-one correspondence between every subset and this number, right, using its binary representation. So we can use that, okay? So let's quickly write this particular code, just in case some of you might be still unclear, because writing the code makes it much more clear. So I'm writing it in terms of a function, okay? So we will generate all possible subset sums, okay? So given an n, and let's say vector of integer comma n, so we will generate all possible subsets of this particular array, right? So we of course need an answer array. Now what we do is, for auto v in for integer mask is equal to 0, mask is less than 2 to the power n, right? This is how you can simply write 2 to the power n. Don't directly use powers and other things. Like if it's 2 to the power n, it's better to write this. Even in pow, if it's completely integer, you can use your own made function, okay? Now mask plus plus, so these are now iterating on all subsets. Now we want to find whichever mask we are currently at, what is the sum of the elements, right? So let's call that subsum, okay? J is less than n, j plus plus, okay? If if mask and let's say 1 to the power j. So if the jth bit of mask is set, then we take a in the subset sum, we add the contribution of a of j, right? And then this subset sum is one of the possible answers after for this particular mask. So we just add that to the answer dot pushback subsum, right? And then we can return the answer. So just to like keep it in order, we just short it once. I will just show you that anyways, that doesn't change our complexity. Okay, so this is the complete code. Let me just show you. So what is the complexity of this particular part? First of all, like this generating all subsets and adding them to a vector, what would be the complexity of this particular part in terms of n and yeah, it's n into 2 to the power n. It's not directly 2 to the power n, because for every mask, for every 2 to the power n numbers, we are looping on n, right? N different positions. So it is n into 2 to the power n, right? So for all of them, it will be like in total, it will be n into 2 to the power n. Now, how many different answers will we get? Like how many elements will be there in the answer in worst, like in total? 2 to the power n, right? So if there are 2 to the power n numbers, if we use the n log n sorting algorithm, what will be the time taken? 2 to the power n log of 2 to the power n, right? So that would give us a simple n 2 to the power n. So this sort will also take us n 2 to the power n, right? So anyways, that's not gonna affect our time complexity. Like it's same as the other part. So sequentially, if there are two same things, it's the same, right? So we're sorting it just to print the answers and see what's happening, right? So let's say we have n, like let's quickly create a test case. N is equal to, let's say 1 2 3, and vector v is equal to, let's say, sorry, n is equal to just 3. There are 3 numbers and this would be 1 2 3, right? And we want to just find out all the subset sums of n comma v. Make sense? Quickly run this subset sum of, okay, this should be integer, right? So this basically finds out all the subset sums. 0 1 2 3 will be repeated twice because there is single 3, and 1 plus 2 equal to 3. There are two subsets which has 3, so that will be there. Make sense? Now this is n into the power n solution. Okay, now let's talk about the next version of the problem. Now we have the same problem in our at our hand, but what we have changed is in the limits constraints, that it is now up to 40. Okay, so let's say there are n numbers, and the problem is same. There are n numbers and we need to find the number of subsets which has sum less than equal to x, but the number of numbers is now less than equal to 40. So now we can no longer use 2 to the power n solution, because 2 to the power 40 is quite large. So 2 to the power 20 is around 10 to the power 6. So 2 to the power 40 would be around 10 to the power 12, which will never pass. Like this will never pass. So we have to do like better than 2 to the power n. So how can we optimize in this particular case? Any ideas? Then use meet in the middle. Okay. Yeah. So we will discuss the idea of something called meet in the middle. Let's talk about what this meet in the middle is. Let's say, let me first of all like give you an overview of what we will be doing, like overview of meet in the middle idea to solve this particular problem for 40. Okay. So we have a problem instance where you have a size of 40, right? There are 40 elements and you need to find all subsets and find out the answer. Okay. So there was one way in which we could have done this is by creating 2 to the power 40 elements, like all generate. So we have our subset sum, right? Subset sum like function which creates all 2 to the power 40 elements, and then we could have like just ran a loop and find out the numbers. But anyways, this is not possible. Like this will eventually like TLE, of course, like this will TLE, right? This is not possible. This much complexity is not possible. So we will look at another way to solve this problem. So what we will do is we will like break this off into two instances. Okay, each having 20, okay, 20 elements. So there are 40 elements over here, right? So create two arrays which will contain like the same elements, but which will contain those 40 elements, but like one element will only belong to one of the arrays, right? So it's like let's say you have the set 1 2 3 4, okay, and then you split it into two parts, 1 and 2 and 3 and 4, right? You just divide into two equal almost equal parts. It might not be exactly equal, it almost equal parts, right? Now what we can do is we can run a subsets, like all subset sum generation, like the method that we wrote just now, to generate all 2 to the power 20 terms and subset sum to generate all 2 to the power 20 terms for these values, right? Now, if we had to generate this subset sum, you can see that there is a one-to-one correspondence between this set and a Cartesian product of this set, these two sets that will be generated. Okay, let me explain what I mean by that. Let's say after this generation, you will have some element over here in this set. There would be 0. I'm just writing the subset sums for all these 1, 2, 2, 3, right? These would be the subset sum over here. For these, the subset sum would be 1, 3, 4, 7, right? Now, if we had to merge to find out all the like 2 to the power 40 different values that are possible, it is nothing but take one element from this, take one element from this, and add their sum to another set. Okay, add their sum to another set. Like take one element from this, take one element from this, and add their sum to one set, right? AR of I plus AR of j. Make sense? So if we take 1 and 4 randomly, yeah, static also works. Like you can like we will look into that how we can do that. You can just put alternate numbers and things randomly. Yeah, that's fine. We just want them to almost equal size. Randomly might not help us a lot in the time complexity. So we want to be like n by 2, like floor of n by 2 and steal of n by 2, something like that. Okay. So you can just put them alternately in the two arrays. Now from this 2 to the power 20, 2 to the power 20, you can take one element from this, take one element from this, and there would be one element in the 2 to the power 40 actual set, which will be equal to their sum. Now, why is that? What is this 1 signifying? That you have taken 1, but you have not taken 0, 2, right? What is this 4 signifying? That you have taken 3, you have not taken 3, and you have taken 4, right? This is the set that we were talking about when this is the sum. Now, from this sum and this sum, if we add them, that means we are generating a set which contains 1, not 2, not 3, and 4, right? So if you see that there are 2 to the power 20 terms over here, 2 to the power 20 terms, and like if you do a cross product, then you will generate all possible masks that would have generated in the original case. Is this clear or not? That if we just do a cross product, by cross product I mean to say like take one element from this, take one element from this, and like add their sum to a set, you will generate this set only. Like this, if you had generated like 2 to the power 40 ones, you will generate that set only, because over in the 2 to the power 20 set that from the top, like this one, every element means some choice for the element that are there in this 20, right? Let's say this we call as set A and set B. Okay, this so for every element in set A, any element in this 2 to the power 20, that let's say call S of A, and this is called S of B. Okay, subset sum array of B, subset sum of array of B, A. Okay, so in every element of S of A means that there is some choice for elements in the A that we have decided, like take one, not take one, not take two. That is this one element, right? Every element in S of B means that there are some choice for elements that are there in B, right? So if we take a cross product, that basically means that we fix on the choices for all elements that are there in the 40, right? Like A and B together. Is this making sense? Is this clear? That if we, let's say, let's take a small example. Let's take that there are two sets, 1 and 2, and one has 3, right? So their subset sums would look something like this: 0, 1, 2, 3, and this would look 0 and 3. So now if you take all pair sum and add those to a array, this will mean that you take, first of all, this is 0, so you will add 0, 1, 2, 3 to the array, and then this is 3, so 3 plus 3 plus 3, 3 plus 1, 3 plus 2, 3 plus 3, right? This will be the whole subset if you take all pairs and add their sum. And if you note, this was the answer for the subset sum for 1, 2, 3, right? So this idea is working. Is this part clear? Why is this working? That why is this cross product actually generating the whole set? Even in terms of size, you can see that this 2 to the power 20 and 2 to the power 20, like cross product, if you remember how cross product works, like if you take S of A and S of B, the cross product size would be like product of that, right? So this would be, in this case, 2 to the power 20 into 2 to the power 20, and that would be nothing but 2 to the power 40, and which means like all the 2 to the power 40 elements are getting generated, right? Okay, so now once we have understood this is the whole like crux idea of the meet in the middle, that we would not be generating this 2 to the power 40 set from this 2 to the power 20 and 2 to the power 20. Like we get to the point of this 2 to the power 20 and 2 to the power 20, but if we loop on like all pairs between them, it's still, we are still doomed, right? Because that's like a 2 to the power 40 operation. We cannot do that. That's a TLE. So we will not generate this. We will not generate this. Instead, we will do the solution of the problem, that find out the number of subsets which will have sum less than equal to x, using these two subset sum generated without generating the whole one. Okay, now let's look at how we do that. So now the problem is, like we know that there are two sets containing 2 to the power 20 elements and 2 to the power 20 elements, and there is some C which contains all pairs of ai plus b of j. Okay, this will contain all pairs of ai plus b of j, and its cardinality would be something around 2 to the power 40. Find out the number of elements x in number of elements sum belonging to C such that sum is less than equal to x, right? This is what we want to find. This is the count of this that we want to find, right? So yeah, so we will use, so this problem I think you might have seen already in one of the 2 pointers of binary search problem. Okay, yeah, so this you might have already seen in one of the problems in 2 pointers and binary search. I personally remember it discussing this type of problem where we had to find the kth element in the C array, in fact. So now we just need to find the number of elements less than equal to some particular sum. So what we can do is we can sort both of them. Like there are 2 to the power 20 elements, right? So we can just sort them. Okay, and then let's say that for every element a of I, like s of a of I, let's say s of a of I. Okay, we know that the maximum element that we can take in the next one would be x minus s of a of I, right? This is the maximum element we can take. So that is going to be nothing but upper bound, right? We know that to find the number of elements less than equal to some value in a sorted array, we can use upper bound of, let's say, the s of b, I'm not writing end, begin and end, and x minus s of a of I, right? So we iterate on other and add the count from the other one, minus s of b dot begin, right? This will be the whole syntax. There will be s of begin dot sb dot begin, sb dot end, but we just ignore them right now. Okay, so iterate on one, binary search on the other. That will eventually, like, so if we do that, what will be the complexity of that? There are 2 to the power 20 numbers in this, and for every number it takes log of 2 to the power 20 to binary search on the other one, right? Because the size of this is 2 to the power 20, so log of that will be taken in binary search. So this would be again 20 into 2 to the power 20, right? For every element 2 to the power 20 multiplied by its log n, right? So this gives us the total count for every element, and if we sum that all for all the elements, we get the total number of like elements over here, this elements that are less than equal to some sum. Okay, so now what is the total complexity of our whole idea? Okay, so what will be the total complexity of this? Can somebody like quickly try that? Total complexity, like considering all the steps that we have done till now. Yeah, so n by 2 to the power n by 2, yeah, it's not n, right? It's 2 to the power n by 2. So yeah, we are not taking 40. Let's say the size was n, so that this would be nothing but n into 2 to the power n by 2, right? Like we don't want to write, yeah, that's almost correct. So let's quickly talk about why this is so. So this splitting will take you just order 40, like this is order n, so this is like just a simple splitting. Okay, now here we pay a cost of n into 2 to the power n by 2. Okay, so I'm removing this by 2 because anyways in complexity divide by 2 does not matter. Over here as well we will do n into 2 to the power n by 2. Okay, now these two parts are parallel. So like this is like sequential things that we are doing. So it will not get product or something like that. We just add them, right? Now, after once we are done with this, there comes the last part that after generating this. So remember, this is the complexity to generate and sort as well. Okay, so once we have this SNA and SFD is sorted, right? So that's why we wrote in sort over there. And next we have uh, in this particular part for every element we discussed that this is going to 2 to the power 20. So this is nothing but order of n into 2 to the power n by 2, right? So it's directly uh, order n plus everything. So order n is anyways irrelevant. So it would be order n into 2 to the power n by 2 in total, right? The total complexity for this particular problem would finally boil down to order n into 2 to the power n by 2, and which will pass because n is 40. So this would be around 4 into 10 to the power 4 into 10 to the power 7, right? This would be around 4 into 1. That will pass. Okay. So instead of having like two brute force, like a big bulky brute force, we divide into two parts. We just individually ran a brute force, and then instead of merging them using a cross product, we did that efficiently for the particular problem. So this is like a condition that where we can apply meet in the middle. Like, of course you can you have to divide and solve individual problems, okay? But the thing is, for the problem like the statement that is given, that whatever you need to count, you need to have some method which, given a set S of A and S of B, should be able to solve for the, like, in the cross product, find out that particular thing whatever you want to search for in less than like mod of SA and mod of SP, right? If you can do that in less than that, then there is a possibility that it can use brute force. Or else, if we could not optimize on this part, like this over here, where you had to do a cross product, and instead of cross product we just used a upper bound, right? Instead of, if we could not have optimized on there, the complexity would still have been 2 to the power 40. So that's not relevant. That's not going to be relevant in any problem, because 2 to the power 40 is not going to pass anyways. Like, it's not going to pass on anywhere. Okay. So this is the part where you need to look into that. Okay, can we optimize the problem? One more thing, that these two separated sub problems should be like mergeable. Okay, so that, like, in this particular part, from here we said that okay, every element over here plus every element over here formed element over here, right? That should be some sort of true, that should be holding in the problem, because or else how do we merge, right? In some graph problems this might become very non-trivial, that how do we merge graphs and other things, but uh, we will take up those when we discuss graphs anyways. But it's very difficult to like merge random sub problems, right? So we need to design it efficiently. So meeting in the middle comes in quite handy in a lot of brute force problems. So finding cliques, like in graphs as well, there are complex problems like cliques and independent sets that can be optimized to like 2 to the power, like, so like all those problems which we can solve with 2 to the power n, some of them can be optimized to 2 to the power n by 2 using meet in the middle, right? Some sort of like that. So there are hard problems of graph, some like hard problems of even like NP complete problem like lamp stack or other things can be optimized using meet in the middle in some sense. Okay. So you need to just understand how do we apply meet in the middle. Okay. Now a quick indicator of meet in the middle for problems when you are solving it in some platform would be having this value 40 or less than equal to 40, right? Whenever you see that something is less than equal to 40 and you can solve it for less than equal to 20, it is a good indicator that this problem can be solved using meet in the middle, right? Because it's obvious, like someone like is trying to ask you to solve it for double constraint, so something n by 2 is desired from you, right? So make sure that as soon as you see some constraint from, let's say, 20 to 40 in this range, you should, your like mind should be okay, meet in the middle is one possible option, I need to explore that, and then you need to think about, can I like do this thing over here in whatever we discussed just now, right? So if we just quickly look into the code of this as well, like that, it will hardly take much time. So let's solve the code as well. So we will create two arrays. So I'm just removing n now, a and b. Okay, let's keep n. So what we'll do is, for integer I equal to 0, I is less than n I plus plus. Okay. If I mod 2, if I is odd, then we put it inside a. else b dot push box. So we are creating the two arrays. This is how you can simply create it. You don't need any randomization in that, because anyways the complexity is bounded, right? There is no like added advantage for randomization. Okay. So once we have the a and b, we can quickly generate s of a equal to subset sums of a size is first, so a dot size comma a s of b will be equal to this, and then you can simply like write a. So make sure that you keep long in this case, because individually they might be satisfying the size 2 to the power 20, but the count of answer can be 2 to the power 40. That is more than integer range. So make sure you check that. Okay. So individually each of the numbers will be in the integer, but the sum can be up to 2 to the power 40. So we need a long over there. And for every element in S of A, we will iterate and find answer plus equals to S of upper bound S of B dot begin, S of B dot end, and there has to be some X. So let's say X is equal to 5. So X minus B, right? And minus S B dot begin. And this should give us the total answer. So I'm generating the full set as well, because in this example we can. And after splitting, we will print S of A and S of B as well, just to have a quick check on how this is working. And then the answer is of course there. Okay. It seems to be off on this. So X was given to be 5, right? X minus B, second. Answer should have been equal to 7. So for 0, this should count. Just a quick check on things. It should not be equal to 7. It should be equal to 6, I think. So right. So for this, yeah. Okay. So number of elements, yeah, number of elements is less than equal to 5 is 7. So that's correct, right? So it's basically you divide this particular set into original set into A and B. First one contains 2 and the other one contains 1 and 3 in an alternate fashion, and then you generate their full subset. Okay, so now you can see that cross product of this will give you this set, and you can like quickly like move on to the first element and binary search on the other. So for 0 there are 4 elements which are less than equal to X. For 2 there would be 3 elements, because 2 plus 4 would be 6. That's not possible. So we can only get 3 elements, and in total there are 7 elements, 7 subsets which will be less than equal to X. So is this problem clear to everyone? Can I have a plus one in the chat? If there is any sort of unclarity, you can ask. Okay. So that's most of like the whole idea for meet in the middle. We will talk about meet in the middle towards the end of the session if we get time, because like the major idea is this only. Every other problem is some manipulation of this. So we will move into the next techniques, and then we will, if we get time, we will come back to meet in the middle and talk about more problems and how we can apply meet in the middle to those. Okay. Because every problem is more or less this, that you have to split it into two parts, solve them and merge them. So every problem, so just that you need to know how to solve this merge part efficiently, because this is some problem you have already seen, in some problem you might not have seen that problem. So that's the problem solving part and identifying it as meeting. Okay. So this is the whole idea of meet in the middle. So we now covered we now know what meet in the middle is, right? So let's talk about one quick miscellaneous technique. Okay. So let's say you are given an n-sized array. So this is obviously now a common statement. So whenever I write this, you can assume that there is an n-sized array and there are n numbers given to you. Okay. Now in this problem, of course, we're not talking about meet in the middle of brute force. This is up to 10 to the power 5. Okay. There are 10 to the power 5 numbers given to you. So now you need to find out, print a subarray with like summation of L, like print a subarray, let's say it's from L to R, okay, such that I equal to L to R, sum of A of I, mod N, this sum mod N is equal to 0, okay. So basically print any subarray that you can find in the array, at least one subarray, such that the sum of the subarray is divisible by N. Is the question making sense? That you have to print the subarray, okay, you have to find the subarray. So the answer will always be a subarray, okay, like you have to print the elements. So let's say we talk about there are 3 elements, 1 1 2, okay. So you can take these 2 elements and you can say that, okay, this is the subarray which is divisible, okay. Keep prefix sum mod n, prefix sum mod n, okay. So yeah, prefix sum mod n, I hope this problem we have already discussed this particular problem. I think this was in some contest as well, that you have to find out the number of subarrays with L, like with modulo n to be a particular value, right? Now the question is, prove that an array always exists. So you need to prove that at least one subarray always exists such that it is divisible by n. How do we look? Yeah. So that's the whole idea, that so we can use Pigeonhole principle for this particular problem. That, okay, if you remember how we used to calculate this particular part, let's talk about that first. So initially we used to keep something like a map. So in this map, what we can do is, initially 0 is present at -1. So remember 1 1 2. Let's run it on a sample itself, so that will make much more sense. So we have to prove that it exists. So let's take 1 1 2. Okay, this is the array. So what we used to do is we used to create a map, and we will instead of storing the count, now we will store where was the last position this prefix sum was available. Okay, so map of 0 is available at -1. Map of, then we come at this position, the prefix sum is 1. So map of 1 is equal to, at position 0, map of 2 is like the sum up to this is 2. So when we are talking about sum, we are talking about sum, prefix sum mod n, okay, prefix sum mod n, okay, up to 2, this up to this the sum is 2, so 2 is present at index 1. MP of, then we come to this position, prefix sum of up to this would be 4 mod 3 is equal to 3, we is equal to 1. So we see that MP of 1 is already present in the map, so we can say that, okay, from this particular index to MP of a 1 plus 1, from this index to the ith index that we're talking about right now, if it's already present, then this would be not MP of 1, this would be MP of ARR of I. So let me write exact expression. From this range to this range will be a subarray that will be divisible by n, right? Now, why is this always possible? So if you think about the number of prefix sums that we have over here for index 0, like index -1, 0, 1, 2 up to, you will get n different at n minus 1. So this is for index 0, this is for index 1, index 2, and so on. So we will get an index for n minus 1. So there are n plus, so this would be some n, okay. So there are n values plus 1 value, n plus 1 different values that you are seeing, right? N plus 1 different values that you are seeing. But the value of p sum mod n can only be from 0 to n minus 1, right? There are only n different values that are possible for this prefix sum mod n. So, and there are n plus 1 total values, and each, like, all of them can be only from 0 to n minus 1. So we can say that at least two of them coincide because of Pigeonhole principle, right? So as soon as we know that, okay, two of them coincide, we can say that, okay, whatever is the subarray between those two positions, like at least one exists. So whichever two is like same, whatever the subarray between them exists will be a valid subarray for the particular problem, because the sum would there be divisible by n, right? Is this clear to everyone, this particular idea? That why is it always why it will be always present, like why is this always present? So this is like one like small example of why where pigeonhole principle comes into play. Let's talk about next miscellaneous trick. So let's say there are n numbers given, okay, and you need to find out, there are two inputs, n and m, okay, and there are n numbers given to you, a1, a2, so on up to an, okay. Now you need to find the product of a of I minus a of j's modulo. Okay, so you take every pair, something like this: I is greater than j and is less than equal to n, right? I hope you know this notation, that like every pair's difference, absolute value of that, take a product of that, okay, and you need to find this particular value modulo m. Okay, so these are given, and the constraints are up to, let's say, 10 to the power 5, m can be up to 1000. Okay, this is the like constraint. So this is given to you, and you need to find this particular metric for the whole array. Make sense? And each of the numbers also, like let's say a of I also I need to give a constraint. So a of I will be up to 10 to the power 9 and from 0. Okay, this is the range. So how do we find this particular metric over here? So this is our answer that we want to calculate, find out this number, like this modulo sum m given as input. So the question is, there is a n sized array given to you. Find out all pair differences absolute values product. Okay, like for every pair, take the difference, take its absolute value, and for all such pair, take their product. Find out that modulo m. Make sense? Like, and m will be an input, n will be an input, and a of I will be input. Their constraints are given to you as this such, like 10 to the power 5, 1000, and this. Okay. So think about this problem for a minute. I think just like if you have the solution like ready, just don't type it. Like you can type it, keep it typed, but don't directly give it. Let other things a bit. This is a good problem to think about. Okay, so take 1 or 2 minutes and think about this problem. How can you solve this particular problem? Okay. So if you have your answer ready, just like keep it typed a bit and wait for some more time before I say. Okay. So we'll take at least 1 minute, maybe 2 minutes to think about this. Not necessarily. M is not like, there is no such constraint given, right? So you cannot assume that. Why will M always be less than N? So M is less than equal to 1000. It's a dynamic input. So of course we cannot like brute force directly because there are 10 to the power 5 numbers. So one more minute. Think about it. How? So in general, you are given modulo pretty large, 10 to the power 9 plus 7. Why is suddenly the modulo so small? Can that help you in this problem? Think about it. Like these are some striking factors that should hit you as soon as you see the problems. That why in general the setter could have given a 10 to the power 9 plus 7, but he has given a modulo some small number. Why is that? Okay. So any ideas how we can solve this problem? M plus 1 values of what? I'm not really sure. Modulo. Yeah, so 0 to m, 0 to m plus 1, 0 to m minus 1. Yeah, the main observation is what Nikhil has said, that answer is 0 if n is greater than m. It's not like m plus 1 values possible. Yeah, n possible values. No, n choose 2 is greater than m. No, that's not true. N choose 2 greater than m does not necessarily, like that's like a smaller condition, because multiple pairs can have the same different value, right? We cannot use pigeonhole on, just a minute, we cannot use pigeonhole on the like the terms of the expression over here. This is not directly pigeonholable, but the thing is we need to talk about when this becomes 0, because there is a product, right? So when does this become 0? When a of I mod m is equal to a of j mod m, right? So as soon as this hits, the answer would be 0, right? As soon as this happens, the answer is 0. Now how do we know that this happens? Because it's mod m. So every a of I, if it is not 0, that means none of them is same, right? That means each of them should be like different, and there are only like m different values available, right? So there are m different values available for each of a of I. Now as soon as two of them become equal, you get one of the terms to be 0 and the answer is 0. So in fact, if n is greater than m, like if this is the condition in the input, just straight away print 0, because we know that's going to happen. Okay. Or else what you can do is run a order n square algorithm. So you can just run on all pairs. If this is not true, then n is less than equal to 1000 basically, and in that case we can just run 2 loops and just find this metric. Okay, like just run 2 loops and find abs and take product in a variable. That's it. So is this clear? How is this working? So these type of things, like this is one example in which like pigeonhole principle can be like realistically applied, right? So the previous one was a bit simpler. This one is like a real question that can appear in any context. Is this clear to everyone? Why is this happening? Why is this? Why? How are we applying to the pigeonhole principle over here? Okay. So pigeonhole principle is done. There are few more. There are similar applications. Like you need to just be careful that a problem can have pigeonhole principle as an observation in the problem. That's it. Okay. So this is one miscellaneous idea that comes up. It's not very often, but there might be some problem which uses pigeonhole principle, right? So it's good to have that in the back of your mind. Okay. So now let's talk about. So basically, in such problems, just think about how many different values can it take, something like that. If you just once think in that direction, this becomes obvious, right? That okay, this is problem. Does it depend on whether the elements are distinct or not? If two elements, so the things are elements needs to be distinct. In fact, their a of I mod m should be distinct, or else the answer will be 0, right? If they are not distinct, anyways, the answer is 0. Even if they are distinct, but their a of I mod m is same, then also the answer is 0, right? So it does not depend on whether they are distinct or not, as long as this condition does not hit. So for this not to hit, there are only order m different values possible. So n can be up to 1000. Okay. So then let's move to the next technique. Wholesome. Like this is all about pigeonhole principle. Let's talk about the next technique. So the next technique that we're going to talk about is like one of my personal favorite techniques that I use in a lot of problems. So we will start with the problem itself. Let's see how we can look into. Okay. So we'll come back to segments that we were talking about initially in some of the problems in STL. So let's say there are n segments given to you. Okay. And each of them can be denoted by L of I and R of I. Okay. So I mean to say, let's say there is a number line. There's no need of this line. Okay. Let's say this is the number line. Now there is a segment from here. Just taking a small example. Okay. So let's say these are some random value. This is 1, 2, 5, 6, 9, 10. Because these are numbers. Like this is not like to scale. Okay. Like the given diagram is not to scale. Now with these settings, like there would be like a segment 1 to 5, there would be a segment 2 to 9, there would be a segment 6 to 10, right? So these are the three inputs for this particular input, right? This is one sample case. Okay. Now what we need to find out, there would be also an input which is given to you, which is called k. Okay. And you need to find out the length of the region on the line which are covered by greater than equal to k number of segments. Okay. So you will be given an input as well, like there is a k as well, and k is less than equal to n, of course. Okay. Now you need to find the number of like the area of region on the number line which are covered by greater than equal to k number of segments. Okay. Make sense? Now this would be fairly easy to solve. So we would be doing it in a bit tougher sense. We would be finding it for all k from 0 to n. Okay. So let's say we need to find out for like for let's say for 0, how much of the region on the line. Let's say let's not take 0, let's take from 1 because 0 would be unbounded, right? From 1 at least it's bounded for sure given an input, right? So for 1, how much portion of the segment is bounded by greater than equal to 1 segment? Okay. For 2, how much of the segment line is covered by greater than equal to 2 segments? And if we try to calculate that, 3 for greater than equal to 3. Now for this example, greater than equal to 3 is of course 0 because no portion is covered by more than 3 segments. For 2, the segment that segments covered by 2 would be this 2 to 5 range and this 6 to 9. So this length is 3 and this length is 3. So total length is 6, right? Now greater than 1 would be from 1 to 10 in total over there. So this would be 9, right? So this is what you need to find out. Okay. Is the question clear? Like this is the whole question. Find this for all like values from 1 to n. Okay. And there are n segments. Now let's talk about the constraints. Now let's talk about the constraints and then partial sum won't be relevant anymore directly, at least. So n is up to 10 to the power 5, k is up to 10 to the power 5, k is less than equal to n, and li can be up to 10 to the power li comma ri. Sorry, we should write the constraint in this fashion that 0 is less than equal to L of I, is less than equal to R of I, is less than, of course, is equal does not also matter in this case, is less than equal to 10 to the power 18. Okay. Yeah, we can do some sort of like that. We'd be doing something similar. Yeah, that's like quite the most of the idea, but we'd be doing it a bit efficiently. But like the idea would be the same. Okay, let's say we just have this particular constraint. So partial sums is not relevant directly. Okay, so we need to find the number of portions for each section. Okay. So calculating greater than equal to 2, first of all we need to calculate exactly equal to 2, and then it will be for like fairly easier compared to that. So the idea for this particular problem that we'll be using is something called sweep line. Okay, so what we'll be doing is we'll be starting a line from minus infinity, and we would be like visiting over this point, and we know that as soon as we visit a starting point, my count of active segments becomes +1. As soon as I visit this point, my count of active segments becomes +1. As soon as I visit this line, my count of active segments becomes -1. As soon as I visit this point, my count of active segments becomes +1. As soon as I visit this, -1. As soon as I visit this becomes -1, right? So now you can see that, okay, as soon as I visit this, my current count is 1. So from this 1 to this 2, this whole region is covered by one segment, right? Now, as soon as I visit this line, my active count becomes 2. So this region over here is covered by two segments. Okay. Now, as soon as I visit this one, I get a -1. So this part is covered by one segment. As soon as I visit this point, this part is covered by two segments. And as soon as I visit this point, this becomes covered by one. And as soon as as soon as I get to 0, we don't need to consider anymore, right? So if we look at these numbers, we can see that, okay, for each of the portion, you can easily count how many segments is covering that particular portion, right? Is this making sense? That if we, so this is some sort of partial sum idea itself, that we have a partial sum, but keeping an array for L of I and R of I would not be very relevant. So what we'd be doing is we'd be creating a like a compressed part that, okay, can we somehow build up this, that, okay, this, after this L of I, we visit the next point and next point and so on, right? Because everything in between 2 points is going to remain fixed. Like there is no point that is changing. So there is, if there is no ending and beginning at in the in between, let's say there is some segment. Okay, what I'm saying is the property that we are using is if there is a segment from A to B and there is no starting point and ending point in between, so the number of active segments at A will be equal to the number of active segments at B, right? So that's just something that we can use in this particular problem, that, okay, when we get from a particular start to the next start or end, uh, from a particular start or end to next start or end, the number of active points is going to be fixed. And if we visit it in a sorted fashion, we can keep a count of how many of them are currently active. Okay. So this idea of this line, so basically we have some sort of line that is getting swept. Okay. So in some sense, there is this line over here. Okay. And that is getting like some sort of sweep like this. Like as soon as we hit this point, we see something, then we hit this point, then we see something, then we hit this point, then we see something, then we hit this point, and then we see something, then we hit this point. So this line is sweeping through the array events. So these are something called events in a sweep line. Okay, these like coordinates are called event. So these points are called events. Okay, and events happen at some point. Make sense? So for this, we can just quickly build up the events and sort them and like sweep from the front to back. Okay. Is the like idea making sense, that what we are trying to do? That's all. Like we would be showing how, we would be looking into how we implement this, but we would be, so once we get this particular like region count, like for every region we know how many segments are getting, like how many segments are covering that. We can easily calculate this using a, like for 3 we know how much length is covered by exactly 3. For 2 we know how much is covered by exactly 2. For 1 we know how much is exactly covered by 1. So now we can build in some suffix fashion that, okay, for n we know, so for n minus 1 it will be either n minus 1, exactly n minus 1, or greater than equal to n, right? So we can build it in a suffix some sort of suffix sum. But forget about this. Is this idea clear, that how we are be sweeping on the line and building for each segment how many segments are covering it? We'll be coding this, but just the idea, like how is this working? Okay, so let's talk about how we can do this in code. Now this particular idea is a very useful idea, and it can like solve a lot of different problems that are relevant with segments or some such kind of events, in competitive, in even in interview or like coding test problems, because a lot of such problem, let's say you are given n segments, find their union, find their intersection, find their anything, like, so if for every portion you know the count, you can calculate anything, right? So let's talk about how we code this particular problem. So this is like a one technique that can like conquer them all, okay, together. So let's say we are given n segments and we are given some sort of L and R. So what we'll be doing is we'll be creating something called an event array. Okay. So it's up to 10 to the power 10, 10 to the power 18. So we'll be needing long. And just to be safe, I'm keeping every variable in long. Okay. So these are called events. Okay. Now, like for every segment, we put its starting point and ending point in the event array. And for starting point, we do a +1. For ending position, we do a -1, right? And then we will run a sweep line. So for integer I equal to 0, I is less than n, I plus plus, what we do is we put event dot pushback so there are int L and R that we have to take first of all input, right, for that segment. And then at L, we know this should not be integer, this should be long. L comma +1 and event dot pushback R comma -1, right? Okay. Now let's say we need to find, once this is built, we sort the event array so that we can like run a sweep line. And then we maintain a count equal to 0, and then we start looping on the events. Okay. So let's solve the given problem itself, what we were discussing. So let's say we need to count for okay, len covered by exactly some x number of things. So make sure you since it's a local variable, you need to keep it to 0. Okay. Now when we loop from 0 to 2n, so there would be 2n number of events in event, right? So you can just simply write event dot size, or you can loop onto 2n as well, right? Now there are few different implementations that you can follow, but what we'd be doing is we'd be taking this into account, that if there are multiple points at the same particular like value, same particular coordinate. Okay. So let's say there is some event that starts at this and ends at this, right? So in this problem, it is not like a thing that can break the solution, but in some problem it might become. So let's say there is an event over here, and then there are two events at this same point, right? This can of course happen, that something ends at a point and something starts at this point, right? So now if we sort them, you will get something like, let's call this 0, let's call this simple values. Okay. So there will be 0 there will be a +1 at 0, then there will be a -1 at 1 if we sort it in the fashion that we are doing, and then there would be a +1 at 1, and then we would be doing something like, let's say 2 and -1, right? This is the whole array, that event array that we're talking about right now for this, right? Now in a lot of problems, it might be relevant to process all the parts that are of same value together, okay, like that happen at the same point. It's not like we want to calculate one value and then calculate answer. Okay, in this problem it will not be a problem, but in most problems you should try to calculate all values that have the same coordinate together. Okay, like add their contributions to the count together, or whatever thing that you are maintaining. So we will this can be used to solve a lot of different problems. So that's why I'm saying in this problem it's not relevant, but still we'd be following that works for general things, right? So what we'll be doing is we'll be keeping a j variable, which is at I. Now while j is less than event dot size, and event of j dot first is same as event of I dot first. So basically all those points which are at the same coordinate will be neighboring elements, right, in the sorted array. So now we just want to find out the window where all of them are same, right? Sorry, event of I dot first, right? So if jth one is the same as the ith first, then what we do is we add the contribution of j. Okay, so count plus equals to event of j dot second. So if it's a starting point, then it will be a +1 to the count, and if it's an ending point, then it will be a -1 to the count. Okay, first count, and then j plus plus, because we move to the next point, and then I will be equal to j minus 1. So let me tell you what we are doing over here. So what we're doing is we are processing all these points together. So initially I was this is I, this is I, and when we count j will end up over here. Like this is the first point where it's not equal to, right? So did I write second? Yeah, this should be second. Okay. So this is I, and we loop till we hit something that is not equal to I, right? Where first is not equal to first. So we will hit j over here. So what we will do is we will make I this, so that the next loop would start from this position, because we are doing a I plus plus over here as well. Okay. So that's why we are making I equal to j minus 1. This is some sort of 2-pointer that we're doing, but anyways, like let's not think about this as 2 points, but that's somehow what we're doing. Okay. That okay, we keep up to this and then we move I up to this, and then next iteration I will start from this. Okay. So we know that like all these points over here in this range is the same value. So we need to add the contribution. Like now after this 1 up till 2, this is going to be same, because like there is no point starting and ending, or there is no segment starting or ending in this region, so the count will remain same. So the whole contribution of this region can be added to whichever point is considered, whichever like thing is relevant. Okay, whichever number of count is relevant. So what we can do is after this point, like we make I equal to this, and we like len covered of, so the length the segment length seg length will be equal to, let's say, event of whichever event we are currently at, I plus 1 dot first minus event of I dot first. So this is the next event minus this particular event, and then this particular seg length will belong to len covered by count number of arrays, right? So this is how much it will cover, right? This length would be covered by count number of arrays. So we are building how much length is covered by exactly count right now, and then we will do a suffix sum to get greater than equal to count. Make sense? Uh, uh, Not really that, because we are already, we have updated I over here. So j plus 1. So j is the first point where it's not equal to this. There is one mistake in this code. I will, after this we will take up that, but I think j plus it will be I only, because we are updating it over here. Okay. Yeah, the starting, so the contribution of all the points from starting point to the end point has been added to the contribution, because j starts from I. So the first points, whichever the first point was, it was same as itself, so its contribution was added, and then we moved to the next point, right? And then we moved so up till the point where it is not same, and then we moved, yeah, exactly, to last j for second. Should take from first I to last j. Yeah, so you can also take this as something like this. So what is the, like, taking this and taking this, I minus j minus 1, and after doing this is all same. These are all same things. These three lengths are all same, because that's what we are looping on, right? From I to j minus 1, it's all the same value. So I and j minus 1 are same, and I plus 1, after doing this, I plus 1 is j and I is j minus 1, right? So this is what we are writing. So all of them are same. There is one small thing that you need to take care of, that what if the element that you reached is the last element, right? What if this does not exist? Make sense? So in that case, we don't add the answer. So this thing only happens if, let's say, I is less than, I is not equal to event dot size minus 1. Okay, if I is not equal to the last element, then only we do this particular thing, that we calculate the segment length and then we add the corresponding segment, right? Now once we have this, what we can do is we can run from I equal to n minus 1 and do a len covered at I plus equals to len covered at I plus 1, and that will give us the answer that we require. So that's the whole answer build up, right, for every I from 1 to n. Is this part clear? So this is the whole code, and I think, like, if you just understand this particular code, you can solve any sweep line type algorithm. Like, it's all the same. Just design the events, design what you do at the event, like save that over here, okay, and based on where you are from this event to the next event, add its contribution to whatever thing that you are maintaining. Okay, that's the whole general idea. Is this clear to everyone, what we have done in the code? Can I have a +1 from everyone if that's clear? Like, because this is an important technique, and like this is not very frequently used in a lot of problems, but once, like, this is at least the more frequent than meet in the middle and the other thing that we, like, Pigeonhole Principle that we discussed. And once you get a hang of it, I think a lot of greedy algorithms will become very easy. Okay, which loop? This particular loop, while j this, yeah. So this is nothing but, let's say there are, let's say, multiple segments that are starting at the same point and ending at the same point. Okay, so you want to, like, somehow process all these points together, because you don't want to miss out on like, you don't want to process the things between these, right? Like, it's not, there is no feasible region between these 2 points, so you want to process all of them together. So basically what it has is, there would be a lot of minus ones and there would be a lot of plus ones, so you want to process all of them together in this. So that's what we are doing, that this is I initially, we are building j to this, and then we are increasing j till it's all same. So we are basically finding the window which is all x. Okay, make sense? Now once we get this, we, like, while increasing, we just maintain this count that we are activating using this count that we are given. And then once we have this, we can just finally find out the answer from this I to j, or you can say from this to this next point, because from this the next point would be this. For this region, whatever the answer is, with that answer you can get the, like, contribution, and then make I equal to j minus 1, because we want to make I equal to j, but there is this I plus plus in the loop itself, so we can make I equal to j. Is this clear now, Aditi? So even if in this problem you just did I and I plus 1, it would have worked for this problem, but it's generally better to write the code in this fashion. Okay? So it's better to learn something that, like, works for every problem rather than just for one problem. Why did you say we do not process because all events in the setting would cause error because segment length would be 0? Yeah, because segment length would be 0. So anyways, the contribution would have been 0, right? And at any point, the number of count will never be less than 0. Like, it will at least decrease and then increase. So it will never be less than 0. So count will also be possible. So it will not matter in this problem, but in general, you should handle that. Okay, because in case you are maintaining some sort of multiset or something like that, that might be relevant. Okay, let's talk about next problem. Let's say you are given n ranges. Okay, each of the range can be like something like L, R, and X. So now let's say you have some sort of range, like a big range, and in that there is a segment from L to R. Okay, and that segment has a value of X. Okay, this segment has a value of X. So this is the value of segment. Okay, so there are a lot of such segments. Like each segment has different value. Let's make a sample case, and again we'll be using the same type of idea. This type of idea that has some 1 or 2 covered. Okay, and now let's say this has the value 1, this has value 2, this has value 3. Okay, now after this, like all these n given to you, there are q queries. Okay, and each query will be of the form question mark y. Okay, now what this query wants you to find is, given at a particular y, at a particular point y, find out what is the maximum valued segment that crosses that particular point. Okay, what I mean to say is, at a particular point y, find out what is the maximum possible segment. Maximum possible segment, I mean to say by maximum possible value of a segment that covers that particular point. Okay, so there will be q search queries, and n is up to, let's say, 10 to the power 5, q is up to 10 to the power 5, and L and R can be up to 10 to the power 18. X can be anything, like X is also 10 to the power 18. So let me repeat the question once more. There are n segments on the number line. Their L and R are given. Both points are inclusive, right? So it's also active at the endpoints. Okay, that segment. Now, with these segments in place, there would be q queries. For each query, find out at a particular point y, which is the highest valued segment active at that particular point. Does the question make sense? X is the value. X is the value of the segment. So we are talking about every segment has some value, right? This segment has value 1. This segment has value 2. So this segment can have value 9. This segment can have value 11. This segment can have value 13. Okay. Make sense? So let's say if I query at this point, we can do that. We will be talking about, we will be using a different technique, which can be relevant for some other problem. Okay. This is possible, but we'll be using another technique. A bit more complex maybe than this, but that would be helpful in some other problem. Yeah, endpoints are covered. It's inclusive. So we can solve this particular problem similar to the previous approach, but we will do it in a bit different way by using one more miscellaneous techniques, because I want to explain that through this problem. It will not be much more complex, like maybe one or some more bit of extra work, but still that's an important technique that you should learn. So you might have already got a sense that this is also some sort of sweep line like idea that we need to use in this. But instead of like having like the count of segment active, we need to keep like what is the highest value active at a particular point, right? So there are two variations to this particular problem. One is online and offline. So now I'm explaining this technique, this particular idea of online and offline. Okay, this is going to be relevant with a lot of questions of queries. And so a problem of queries is called online if you have to answer the query and then only you get the next query. Okay, so in some problem, let's say you ask the question asks a query, and then once you get the answer, once you like print the answer, then only you will get the next query. So in such problem, what they do is they use some sort of like encryption, that whatever the answer for the first query is, the next y would be, let's say, the answers or some given value. So unless you get the answer, you cannot like find out the next query correctly. Okay, so these type of questions are called online query questions. There are some questions which are offline, which means like all the queries are given to you, like all the queries are given to you in the input, and then you need to find the answer. Okay, so we would be talking about a technique that can be used in these problems of offline query problems, which can help you in some like some offline query problems in to solve it in a different way than online query problem. Okay, so we generally try to see that mostly we have been solving questions similar in online and offline, right? Both of them might have been same till now, but we'd be talking about one technique for this particular problem that would use the property of that the queries are already available, like they are offline. Okay, and by offline I mean to say that I already know the queries, I just need to print the answers in the same order, right? So what I'd be doing is I would be keep creating these queries as an event on the line. Okay, so let's suppose let's take one example. This is 1 2 2, this is the point, let's say 4, this is 0.6, this is 0.9, this is 0.10. Okay, and like this I will say point like this. Okay, this is 0.3, and let's say this is 0.9, this is 0.7. Okay, so let's say the input is something like this. There are 3 segments: 1 2 3 with a value of 9, 2 to 9 with a value of 11, and 6 to 10 with a value of 13. Okay, and then there are queries. Okay, q queries, that means there are 3 queries. Okay, there are q queries input given to you, and then we will have queries similar to like this. Like you have a query question mark 3. Okay, question mark, let's say 9, and question mark 7. Okay, these are the queries given to you. Okay, now what we'll be doing is we'll be adding these queries to the event. That, let's say, we will sweep line once, and as soon as we hit a query point, we will answer that query there. Okay, so we will like sweep the line from front to back, and as soon as we get to a point where some query was asked, we will find out what is the most active segment right now, and we will answer that query there. But the thing is, the query might not occur in the same order in which they were asked, right? Like 9 was asked before 7, but if we do a sweep line, 7 will be answered first, then 9. But it's okay because we can save the answers in an array. Okay, let's say 1 2 3 in the query number 1 2 3. So we first hit 3, so we calculate the answer for the query number 1. Okay, and that is, let's say, equal to 11. Okay, then we hit 7, so answer for this query at 7 is equal to 11 is equal to 13. So we save the answer at position 3 because 7 was at query number 3, equal to 11 equal to 13. And then at 9 we can also like keep at 7. So we can build this answer array first and then answer in order. Okay, what we are doing is we are like having the queries, you like take all the queries from the input, save it in some vectors, sort it and work with that, and then build the answers in the order they were given, and then print the answers in that order. Okay, so this is something called offlining the queries. So you basically have all the queries and then use them to solve in whichever order you want, and then like report the answers in the question in the order the question asked. Okay, is this making sense what we are doing over here? Right, so we can like, I hope what I'm saying is like you can make sense of what we can do. Don't think about code right now, we will see how we can do this in implementation, but just think about idea that is this something that is making sense, right? Now once this is there, what we will do is that at every like L, so what we'll do is instead of now maintaining count, what we can do is with the sweep line we can maintain a multi-set. Okay, which maintains the values of the active segments, right? So what we can do is as soon as we hit a L of a segment, we insert its value at the set. Okay, at the multi-set. Then when we hit 2, we insert its multi-set. We hit 3, so we answer the query as the maximum in the multi-set. Then we hit 4, so we remove 9 because this element gets finished. Then when we hit next 6, we insert 13 in the set, and then we hit 7, so we answer the max, that is 13, and so on, right? And we place it at correct position in the this answer array. Okay, that's what we would be doing in the code. Okay. So in a lot of problems, you might not be able to answer the queries online. So it is much more difficult to solve the problem online than offline. Like in this problem, it might not be that much relevant, that why is it so much hard to solve it online. But in some problem, it might be difficult to solve it online. Like you might not be able to find pre-process in some form in which lower bound will work. Okay, in this you can like maybe create these points and use lower bound, but in some problem it might not be able to. You might not be able to build that. Okay. Because we need to find the kth, right? So let's think about this question. Let's if we just if we just change the question a bit, it will make sense. Let's say I ask you this, that in each query you are given y and z, and in this you need to find at a position y, find out the maximum value that you can take that is less than equal to z. Okay, so let's say the query asks that at a position y, find out the maximum the element of the sets that are active at that point. Out of those, find out the maximum value that is less than z. Now if you do it, like if you cannot pre-process and save all these things, right, at every segment what is less than z, and based on that for every less that so you will have to save this multiset at every point. That's order n square. Okay, but if you make a maintenance set that maintains the properties at that set, and then you can answer a lot of such queries over there, right? Okay, so let's come back to the same problem, because this will be a bit more tedious to implement. It's also doable because in set we know how to find out elements less than equal to z, right? So now let's see how we can do this particular implementation. So this would be a bit more like lengthier than the previous one. So now let's talk about how we'd be implementing this, because we need to maintain a lot of different things. I'll be drawing some things over here. Okay, so now events are a bit more complex. There are two types of event. Okay, there is a event which is like activate a segment. Okay, activate, answer query, and then deactivate, right? Deactivate a segment. So in this we have to remove a element, in this we have to insert an element, and in this we have to answer a query, right? Right. Now when we are saying activate, so now what should be like at a point, at a same point, let's say at one particular value, let's say all three of them occur, that there is some segment which is starting, there is some segment which is ending, and there is a query at that point as well. So in which order should we process these events? Exactly. So let's suppose at a point some segment is activating, some segment is ending, and then some segment is we have a query. So all those that are going to activate are also going to influence the query at that point, because we said that okay, L and R are included in the segments, right? So first we have to activate all, then we have to answer the queries, and then we have to deactivate all those that are like at that point which are deactivating. Make sense? Is this making sense? Why are we doing this particular thing? Because if we first like activate and deactivate everything, then the influence of all these segments will vanish, right? So there might be R of some segment which ends at this point, so you might need that to answer. Okay, is this clear to everyone? Right. So now we'll be looking into how we code this. Okay, so like quickly noting that what do we need. So we would be, so since this is something that we have to do, what we will do is we will take this as like event type 1, and we need to insert a value x. Okay, this is event type 2, and we need to query a value. We have to, so event type 2, and at this index we need to like get the answer of ith query. Okay, ith query. And so we will save I, and this is type of event 3 in which we have to like remove x, something like this. Okay, so we just save x, so which means that we have to remove x. Okay, So now events will no longer be as simple as just a LLI. It will be a pair, in fact. Okay, so we'll have to keep one more pair. Okay, make sense? So at L, we know that we activate something at with a value X because every segment has LRX. Okay, so we activate X. Okay, so this is type 3 query, and we remove X. Okay, so we will use these values to detect what to do in the using this particular value, right? And before sorting, we also need to take the queries. Okay, and for integer I equal to 0, I is less than q, I plus plus, seen L. So for every query, you know, you need just you get a value y, right? Question mark y. So I'm not taking the question mark. It's just a value y. Okay. Now with this y given to you, you just need to like event dot pushback. So we need to find the answer at y. So y is the point at which the event is happening, and event type is 2, and you need to answer the ith query. Okay. So we just mark the, because here we will need to store it, right? So we will create another array, value array, answer of query of size q, because in this we will save all the answers when we get them. Okay, because we will not get them in the order in which they are asked. And then we will sort the events. Now note that why did we took it as 1 2 3, because then if we sort these pair of pairs, first they will be like sorted by in the order of their point, but if their points are same, first all the activate points will come, then all the answer points will come, and then all the deactivate points will come, right? That's why we took it in on the order 1 2 3. Is this making sense? Why are we keeping 1 2 3? Because we discussed this, right? We need to first activate so that like influence of this point gets into the multi-set, then we answer queries, and then we remove. So that's why we keep this 1 2 3. Okay, and then we sort the events. So sort works with pair of pair as well. Like it will first compare the first element and then second element, that is again a pair, so it will get pair comparison and so on, right? Now let's say you could have used even like a vector of 3 elements. That's also possible, but it's just an implementation detail, so we did not pay much a heed of to that. So now length covered is not needed. We just need a multiset to maintain. Okay, multiset of LLI multiset. Okay, so we just need to maintain a multiset. Now we will loop through the events. Now in this particular problem, you don't need to process all events at the same point because we have taken care of the order in which they should appear. Okay, so it's okay if you're defining the order in this way, that, and you know that if you process that in that order, it will be okay. So you can take like just process one event at a time. So if event of I, now we will use the indicator. So event of I dot second dot first. So I need to write a lot of things, so it's better to define things. So I'm just quickly defining first as f, and as define, second as s, right? So now if event dot second dot first, so that is like go to second and then it's first. So if that is equal to 1, so that means it's an activating event. Okay, else if event of I dot second dot first is equal to 2, then it's like a query, and or else it's a remove type of thing. So if it's an activate point, then empty dot insert event of I dot second. Okay, if it's an erase, make sure you erase only one instance of that particular value. So erase empty dot find event of I dot second, that particular one instance of that particular value should be removed from the multiset, right? If it's not defined correctly. Okay, just quick check. That's not the problem. S is not getting defined. Okay. Okay. That's how we write define. We need to write F first and then its meaning. Okay. So after this, when you come to a particular query, you just need to find out the maximum element. So uh, of course, it might be an empty set. So let's say we handle empty sets with -1. Okay. So if event if empty dot empty if empty dot empty, right, if it's empty, then answer of, so at a particular point we save the answer at answer query with the index. We have saved the index at I dot second dot second, right? We have saved that over there. So we, at that index of query, we save the value empty dot uh, -1 because it's empty, or else we can save over there the maximum value, and that we can find because it's not empty, so it's star of r begin. Okay, so last reverse begins value would be equal to your maximum value in the multiset. Okay, and that's all. And after that, once you're done with this, now answer the queries from this array in the order they were asked. Okay, so now we will just loop it from uh, 0 I will be less than equal to q I plus plus, and then C out answer query of I and del, right? So they will now answer in the order they were asked. Is this now making sense what we are doing in the whole problem? So we are pushing back the elements. No, this is like we cannot rename seconds and first with using, right? It's not a data type. It's like pair, pair dot second. So so we are renaming this. If you want to rename data types, that you can do using or using type def. You can use type def. This is also a valid syntax, but I personally use using. It's almost the same length, like it's exactly same length. Why not hash define? Because if at it's okay, like it anyways happens in the compiler stage, so it does not matter much. Like you can use hash define, but it's generally preferable to use using an array because that's what they are made for, right? I'm not exactly sure whether there would be some problem or not. I have never used hash defines for data types in general. I used to use type def first, but I personally use now using. But you, because at some point at some place, if LLI is like happening and it might use the hash define to replace that. I'm not really sure if that's a problem, but some place it might be. Okay, so this is the whole code for this particular idea, that let's say you're building the events for every segment. You know, it's either activate, deactivate, at L put X, at R at put the removal event at tree. Then all the queries you take offline, and then for all the offline query you just put there at the particular point, sort the events, maintain a multi-set, and then process through events. So either it will be an activate, so it will first of all come in order, and even if it's at the same point, first activates will come, then answers will come, and then deactivates will come. So just process it in order, insert elements, then like remove elements if it's a deactivate, and or else just answer the query and save it at the index where you had to answer, right? So ith query, we saved the I over here in the pushback of this empty event. So we save at that position the answer. Okay, now we just answer the queries in that order. Is this all making sense? Is this clear to everyone? Can I have a plus on the chat? Okay, so this is a nice idea that can help you in a lot of problems. Okay, so these are just like tools which you can use to think in some problems. This would be this of course is a problem specific technique. Like in that problem this is valid, but in a lot of problems this might be, you can use, instead of using complex segment trees or something like even like query questions where you have to use complex segment trees, you can just simply use sweep line and solve that problem, right, by offlining the queries if you want. Okay, So it's not necessary to use complex segment to solve problems. This is a very nice technique which can solve a lot of different problems if you think about it. Uh, so I think this is all about sweep line. There are of course more ideas on sweep line, but of course we have not covered a lot of different topics. So we will keep on seeing sweep line in 3D problems and other problems when we like encounter them in data structure problems. Okay. So now I think that's all about sweep line. Now let's just quickly talk about some like meet in the middle ideas. Okay, so I talked about meet in the middle in the first, but we did not take up a lot of problems. So now we'll be just discussing few like ideas that you can use in meet in the middle. Okay, just some idea. Okay, so so where can meet in the middle be relevant? So in let's say I'm just going to talk about like ideas without any like code directly. So let's say in some graph, if you want to search shortest paths, okay, we don't really care about the code right now, but like let's say there is some graph. Okay. So what you would generally do is, given a starting point and an ending point, you start the like BFS at a one point, and you whenever you reach the other point, you say that okay, you have found the shortest path, right? This kind of ideas are there, but the thing is, the explode number of points is very large if you use like from one point. Okay, so like let's say there is one point, and then this much of graph is explode unless you hit the T point. Okay, let's say this is quite uniform graph out everywhere. Okay, instead if you use meet in the middle for this, the diagram would look something like this, that you try to find at least one point where you meet in the middle, like you have a shortest path to this and you have a shortest path to this, and then you meet at this point, right? So if you see that like if we generally take like the number of nodes as the area that is kind of visited in this space, so let's say if the graph is large, so in fact this reduces the search space by half, right? So this kind of optimizations are used in meet in the middle. Okay, some more idea of meet in the middle would be, let's say, first like one would be similar to what we discussed. Let's talk about this. Let's say you have some sort of operation. Okay, let's say you are given a string. Let's try to think about this problem. Given a string s and a string t. Okay, there are two strings given to you. So what you will do is you will have a string s, select a sub select, so we define an operation op, okay, which is select a subarray and reverse it. Okay, select a subarray in the string and reverse the array, reverse the subarray. Okay, this is the operation. Okay, so you can do this operation on the string s. Make sense? So you are given a string s, you can do an operation by selecting a subarray and reversing that particular subarray, right? Now after 4 moves you have to build t, like from s you need to check, is there any sequence of 4 moves with which you can reach to t? Make sense? Like after doing 4 subarray reversals, can you make t? That's the whole question. Okay. So when you think about this operation, like on a string of length n, right? Let's say the strings length are n and n. Okay, of course they need to be same length. So if on a string length n, how many subarrays are there that you can reverse? Like how many choices of this operation are there, first of all? Can you quickly write on the chat how many subarrays are there which you can reverse in an array, in a string? Yeah, n choose 2, right? N choose 2. So these many subarrays you can reverse. Now if you do 4 such moves, it would be n choose 2 to the power 4, because you will first take a move and you will generate a new string, then again you will have this many choices, then again do that move, so there would be this many explorations possible, right? So we can, if let's say this is in terms of n, if we can write this as n to the power 8, right? We can write this as n to the power 8, that if n is, let's say, some n, this is n square and this is n to the power 8, right? Now we can optimize this by using meet in the middle in this fashion, that okay, let's say we have s, we do 2 reversals to it to generate a map of all possible reachables map, or all possible reachable strings. Okay, so you have n, like order n square number of strings that you reach on the first move, and then order n to the power 4 moves, or n to the power 4 number of strings that you can reach after second move, right? This is how many choice you have. So create all those strings using recursion and keep it in a map. S1, S2, S3, S4, and so on, right? Similarly, from T, do this 2 times and generate in order n to the power 4. So since the string lengths are order n, saving them in a map would take n log n. Okay, it's not log n directly. Make sure that if you're saving vectors and strings in map, do consider the length into complexity. If they are large, you need to consider that. So like you can just some sort of build a map or hash map or something like that and save them in over here. So it will take something like order n, right, to save over here. Okay. Now what we can do is we can loop on all these order n to the power 4 choices from S and search for the same value in this T, because like any move of 4 length, S1, S2, S3, S4, right, this can be decomposed into like the meet in the middle point, where from T you can reach this point in 2 move, and from S you can reach into this point in 2 moves. So from S you can like take 2 reverses, form all possible subarrays, form all possible strings that are valid. From T, make all subarrays and form all possible strings that are valid. And now if any one of them are common, then you can create from S to T, right? Because from S you can go to that common one, and then from that common one revert, like just invert the moves that you did, right? And you can reach to T. So in that case, you can solve this problem in like n to the power 4 multiplied by n to save in n log n to save each of the strings in a map, plus order n to, so this is for S. Then again the same thing, 2 into this for T as well, S plus T, build this maps and then traverse on one of the maps and search it on the other. So straight away we can drop this down to order n to the power 5 log n, right, from n to the power 8. So total number of choice, get it somewhat halved, right? So these type of ideas might be relevant. So I hope you got the idea of like what type of problems generally like takes meet in the middle into account, right? Like from both sides you can do the meet in the middle. So either you divide the set into 2 parts, or there is some exploration that you are doing. So like there is n moves that you have to do, divided into n by 2 moves, and from both the sides, and then meet at one point. Okay. So these are the 2 different types of ideas that are prevalent. And so comparisons take it's not order log n comparisons, right? To compare strings of length n, it on worst case it can take order n. Is order n map comparisons take, yeah. So there are log n comparisons, and yeah, because that. So you have already written the correct logic, right? Because there are like 2 string comparisons take order n on worst case, right? And there would be order log n number of comparisons in a n sized map. So this would be like 4 into n, but anyways, that's not right. So n length string will take n log n. Okay. So these type of ideas can be there in meet in the middle. Okay. So I think that's all on meet in the middle. So now you will have to solve problems. That's for you. Like that's the practice. But I think we covered most of the techniques through problems in the session itself. So I think that would be all for today's session.